famous chronic relationship. Does everybody know about this, or should I talk about this? Everybody knows? Some knows, and some do not know, right?
I forget, is this the same as Hilbert transform, or is it different?
Right, it's very similar to the Hilbert transform. Physicists call it the Kramer's chronic relationship, but the signal processors call it the Hilbert transform. Okay. So it's the same thing. Let me just go through it anyhow. Say if you have a causal system at a particular point in space, I'm fixing R, fixing a location in space. So I look at the relationship between D and E as a linear system transfer function theory. And then I know that in the time domain, that this is just a convolution of this thing in the time domain. This is convolution of this constellation, okay, by linear system theory. And then I know that this, I'm not going to distinguish between frequency and time domain very well. I'm going to use the same symbol. That the time domain representation of epsilon is just the Fourier inverse transform of epsilon in the frequency domain. Okay. And then I can also write the time domain transfer function epsilon in terms of something that looks like this, so that it converges much better. Converges much better. Plus, if I take this constant now, it just becomes a delta function. Okay. In other words, I'm saying that the transfer function epsilon usually has two parts. One part that can be extracted, which is a constant at infinity and omega equal to infinity. That is the instantaneous response part. This part is instantaneous. Instantaneous. So this usually corresponds to the vacuum part. The vacuum part of the permittivity is instantaneous. And then the leftover part might be molecular or atomic. And that will take some relaxation time for this to occur, and this is expressed in this manner. So you can always express the transfer function epsilon in this manner. And then by Fourier inverse transform, okay, I can go back and forth between the two, but what is more important is that if this is analytic, if this is an analytic function, okay, if this is an analytic function, this is the Fourier transform of the part of the thing that is non-singular part of this epsilon of t. If I subtract this singular part from this, this is just a relaxation part. And this should Fourier transform to something that is analytic. If this is analytic, then I can write the fact that epsilon of omega minus epsilon of infinity, which is an analytic function by Cauchy's theorem, is equal to the integration over some contour that is yet to be defined I'm just writing Cauchy's theorem, which is stating the fact that if this is real, okay, then this is omega double prime, omega prime, okay? And then if I put omega over here, This is not good. This is, if I put omega over here, let me call this real of omega prime. This is imaginary of omega prime. Okay? Then I can say that this function on the left, okay, can be written as a contour integration of this which I call C minus this one, which I call C infinity. If this contour subtracts this contour, it should be equal to the residual contribution from the pole here. Okay, this is analytic. This is just a Cauchy's theorem. Everybody agrees with that. That should be the case, right? That should be the case. I'm just rewriting Cauchy's theorem. So everybody accepts that?
Excuse me, about epsilon of omega. Is it assumed known as 0 or not?
Is it what?
Epsilon of infinity.
No, it's not 0. It can be epsilon of 0, for instance. It can be the vacuum permittivity. Okay, it doesn't go to 0. It's the permittivity that the system would see when the frequency is extremely high. Okay, when the frequency is extremely high, we can assume that there are no relaxation response at high frequencies. So we can say that the response of the system is instantaneous with respect to the applied field. If this is a delta function, okay, this is a delta function, this is a constant independent of frequency. So then the relationship between these two is instantaneous.
Well, as I recall, it should be transparent as the frequency is equally high.
Right, it's transparent, so you don't see any relaxation in the material. You only see the vacuum permittivity. Okay. So I can write something in this manner. I can use Cauchy's theorem to write down this relationship quite easily. I can also evaluate this residual term. The residual term and before I do that, let me argue that I can ignore the C infinity contribution. Okay. I can ignore the C infinity contribution because this contributes to 0 by Jordan's lemma because this decays sufficiently fast at infinity that it will satisfy Jordan's lemma. And also that this thing tends to, that thing when omega tends to infinity also. Okay. So the numerator also decays sufficiently fast so that Jordan's lemma is satisfied. So I can ignore the top integration and just keep only the ray axis integration. And if I keep the ray axis integration, this C is an integration that looks like this. Okay, and I will break this into two parts. A part that looks like this, plus the residual part. Okay, this is what I call the principal value part. The principal value part is the part that integrates to the left just before I hit the singularity, and then I jump to the right and go to infinity again. Okay. So the integration part can be broken up into the PV part plus the residual part. Residual part is just the integration around this pole. And I can actually evaluate the residual part very easily. The residual part is actually from minus pi to 0 d. The residual part, let me just put the residual part first. The residual part is just this part, which is d omega prime, epsilon of omega prime minus epsilon of infinity over omega prime minus omega. And I guess the next thing to do is omega prime minus omega is r e to the I theta. So this change a variable, right? then the omega prime is I r e to the I theta d theta. And then you would have something like minus pi to 0 d theta. Okay? And then omega prime is going to be evaluated very close to omega, so this becomes epsilon of omega minus epsilon of infinity. And then the denominator will become r e to the I theta. And then I should have a I r e to the I theta out here. And then I should have minus pi I, right? It's pi I epsilon of omega minus epsilon of infinity is what I should get. Should be pi I. I should get that. So if I take the residual term out, okay, I can say that this integration is equal to PV part plus pi I, which is half epsilon of omega minus epsilon of infinity. If I take the residual part out, in that manner I get this one, and then take this to the left hand side, I finally have the identity that this epsilon of infinity, epsilon omega minus epsilon infinity equal to 1 over pi I. The PV integration, the PV part, the omega prime okay, I have this identity. Everybody agrees with this identity. So omega is real, both on the left hand side and the right hand side. Omega is real. Okay, omega is completely real because when I do the PV integration, I'm integrating on the real line. So everything is real in terms of omega. So the only thing that becomes complex is epsilon of omega that becomes complex. So if I take the real part and the imaginary part of this, okay, if I take the real part of this, assuming that this is real, this is like the vacuum permittivity, if I take the real part of this identity, I get the Hilbert transform relationship or the Kramers-Kronig relationship. Okay, if I take the real part of this, let me take the real part of this quantity. And then, because of the I here, if I take the real part, if I take the imaginary part of this. Okay, the only thing that can contribute to imaginary part is this term over here. Okay, so because of 1 over pi I, and then it should be 1 over pi, the PV integration of this part, the omega prime, epsilon the double of omega prime. This is one identity that I arrive at. And then if I take the imaginary part of this, I get the second identity, which is that epsilon double of omega is equal to minus 1 over pi PV minus infinity the omega prime. Okay, I get this Kramer-Kronig relationship. Some of you probably have seen this before in signal processing and also in physics courses. All causality systems have to satisfy this relationship. Because we assume that this is a causal system, then there are no poles. No poles here because of causality. Because if something is causal, then when t is less than 0, this has to evaluate to 0. And the only way for that to happen is that this has to be an analytic function in the upper half plane. Okay? And if you can assume that this is an analytic function in the upper half plane, then you can add this contour, assuming that this is the only pole that you have. Okay? And then after you've been able to go through this, assuming causality or that this is analytic in the upper half plane, then you arrive at this famous chronic relationship. The key is that there are no poles up there. There are no poles up there because this function is causal, and this is a causal function. Then you can easily prove that for this to be causal, it has to have no poles. Right? Are there any questions regarding this relationship? Yes?
What if you do the, see how your, the principal, what is that called? The residual part, you went down. What if you went the other way?
Then it cannot have this identity, right? I was saying that this was equal to this because of Cauchy's theorem. I have to include the pole. And there are no poles, no other things that this thing has in the upper half plane because of causality, because it's analytic in the upper half plane. So I only have a choice of going down below it to establish its identity. Otherwise, if I go above it, it would be equal to 0. I guess if you go above it, it will be 0. You have the same thing, right? You take the residual part, and then you still end up with this. What was it? This expression, right? We just take the principal, the residual part on the left-hand side, the minus half becomes minus half, because it takes, let me say it properly. If you have gone above, then this will have a minus sign, this will have half, and this will have a 0. And you take this minus half becomes plus half, and then you will still end up with this identity. So this identity can also be gotten by taking a part that is above. And this is a PV part, the principal value part. And it's always true. Okay. If you have no questions, then we take a 5 minutes break. Okay? Take a 5 minutes break.